This is lesson 4.2, more with log functions. So this is a continuation of working with defining and seeing the relationship between log functions and their inverses, the exponential functions. You might want to pause the video and make note of these 5 characteristics of logarithmic functions that are in the form f of x is equal to log base b of x. They talk about the domain and the range, the intercepts, sort of the basic shape of the graph, and the asymptotes. We did the same thing when we discussed exponential functions. I'm going to skip past the translations for just a minute and look at this. Once again, I think this is a little slide that is so very valuable that you should copy this down and this down. When you have a base that is greater than 1, the exponential function is in blue. This is the growth curve. Its inverse, which is a log function, a base greater than 1, looks like this. You can see that so many things have interchanged. Instead of a y-intercept at 0, 1, we get an x-intercept at 1, 0. These are reflections of each other about the identity line. The growth exponential curve has a horizontal asymptote. See how it's trying to snuggle? Whereas the log function has a vertical asymptote. This drawing shows in blue the exponential decay curve when the base is a proper fraction. Its inverse, instead of going through 1, 0, also goes through 1, instead of 0, 1, goes through 1, 0. It has a vertical asymptote instead of a horizontal. These are reflections of each other about the identity line. They just happen to intersect. Use these pictures in the first 2 questions on your homework. Now I'm going to go ahead and branch off to my math lab because I have realized it's very difficult to see those questions in my printed form. So if I look at question 1, all right, in this, these are in, I believe, either blue and red or maybe green and red. The first one is f of x is equal to 2 to the x. That's a growth curve. Log base 2 of x is its inverse. If you look at these and you compare them to, let me go back, compare them, I should be finding something that looks like this. The colors may be different, but this shape. And it is, I believe, this choice. You could blow that up, and there they are. This is the growth exponential curve, and this is its inverse, the log curve. All right, let's look at the next question. I won't do all of these in the assignment, but it is somewhat helpful. All right, this is also an exponential curve, and its log inverse, but these are both with the base of 1/8. That means that I will be looking for a picture that looks more like this, where the base is a fraction. So going back, we may need to enlarge them to see, and I believe that this is it. It is a little hard to tell, but here is the decay curve. This is 1 because it's 2, 4, 6, 8, 10. So right here is 1. So the blue is the decay curve, and the red purplish is the log inverse curve. They are reflections about the identity line. So it is this choice. It's a little difficult to see, but that's correct. And now I am not going to do all of, let me look for a similar question. I'm not going to do every problem in the homework, but I am going to do quite a few. In this one, I have 1, 2, 3, 4, 5, 6 different log functions. They are all log base 5 of x. Now going back to the notes, whoops, I really went back. Okay, in this part, what is important is to find the log function that looks like the basic log curve. This is when no transformations have taken place. So you need to know what this looks like. You also need to, I'm going to go back to the notes, and you may want to pause the video and write some of this down. A vertical translation, a vertical shift, takes place when you add a constant or subtract a constant outside of the log expression. Sometimes the c will be written in front as c plus logarithm. If you add, it goes up. If you subtract, it goes down. If instead you add or subtract inside the argument, you get a horizontal translation. Opposite direction. Plus will go left, and minus will go, well, I just keep opening things, will go right. If you want to study reflections, if you are changing the sign on the outside, you're going to reflect about the x-axis. It is an up-down reflection. If you change the sign on the inside, you are going to reflect about the y-axis, and it is a horizontal left-right reflection. We won't be working with vertical and horizontal stretches and shrinks. So now if we go back to the homework problem and we want to do the matching. As you look at all of these, and you can enlarge, that might be helpful, but I believe that this one, I don't know where the numbering system came from. This was called number 52. I don't know where that is. This is your basic log function right here. So that would be log base 5 of x. Okay. This one will be log base 5 of x and shift it down 1 unit. Sometimes that is difficult to see. It's going to be the same shape, but it's going to be shifted down 1 unit. And I believe that it is this one. Sometimes this, like I said, is difficult to see. This is a negative on the outside. That means it is a reflection about the x-axis. We're going to take this graph and flip it over. That will be right here. Come on. There we go. This one, it's going to have a horizontal translation. It is going to go to the right 1 unit. And I believe this has moved from an x-intercept of 1 to an x-intercept of 2. Negative on the inside means that it's going to have a reflection about the y-axis. So instead of going over the positive x-axis, it's going to go over the negative part of the x-axis, and that looks like it is right here. Finally, this one has two transformations. It has a negative in front, which means instead of going on top, it's going to go on bottom, kind of like this. But then this is a positive one. You would normally see it as +1 over here. So this is it. It has shifted up 1 unit. We can check those, and we were correct. We're going to do at least one of these. Unlike the last lesson that we had on exponentials, I'm not going to do every single one of these because the process is so very much like what we did with exponentials. All right, it says begin by graphing f of x equals log base 2 of x. Then use the transformation of this graph to graph the given function. What is the vertical asymptote? Use the graph to determine the given function's domain and range. When I see this function as a transformation of the original, I see a +2 on the inside. That means a horizontal shift, and it's going to go the opposite direction. It should go 2 to the left. Now I'm going to graph it. Let's see if I can do this without any mistakes. The log function shape is right here. Where is one point I know? I know that the x-intercept is there. This is base 2, and my problem is base 2, so that's good. I do not have stretches or shrinks, so that means that the coefficients are 1. I do have a horizontal shift, so it is a horizontal shift, and it is, let me get a keyboard accessible. Okay, it is a horizontal shift to the left 2, so I will put -2. There's no reflections, so if I say please do that, then it hasn't done it yet, but maybe if I save it, it will. Okay, but I'm going to go back in. Now, it used to have an x-intercept here. Because of the horizontal shift, it went 1, 2 to the left. Now it wants, since this is a logarithm, it has a vertical asymptote. The exponentials had horizontal asymptotes. So I'm going to draw a line, and it's going to be right along here, so I can pick 2 points. Doesn't matter which 2. It does want that to be a dotted line, and I don't know where it went. There it is. I'm not sure what I did, but I tend to do those things. So I will close that. I didn't save it. Let's go back. That seems to be my problem this time. Click, click, got a line, make it become dotted. Don't forget to save it. There we go. That looks good. Check my answer. That's right. Now it wants to know the equation of the vertical asymptote. It is a vertical line. It is an equation. It is the equation x equals, and you can see -2. The graph is trying to snuggle up against x equals -2. Now it wants the domain. Something to consider is just looking at the graph. It is approaching -2, that's the leftmost, and then it's heading toward positive infinity. So I can choose the open interval notation. It is -2. I learned today from a student that if I tap tab, I will be able to put my infinity or my second value in there in the right spot. I don't have to delete the blue box. Check my answer. The range, open interval. The range is from -infinity and it goes up. Even though it's going slowly, it is rising toward positive infinity. So I will say -infinity, tab, positive infinity. Now, I am not going to do all of the graphs. What I'm going to do is go through the exercises and simply talk about what the transformation would be. In this video, because it's inside, it's going to go left 4. A horizontal shift -4, left 4. You would then find everything else that you needed to. This one, because it has a +6 on the outside, I know you're used to seeing it over here, but it's okay for it to be over here. It's going to go up 6. All right, and then you would continue from there. Well, I'm just going on. Okay. What would this one be? It is on the outside, because if it were on the inside, there would be parentheses. So this is down 3. Now we have a few questions about domain. I'm going to go back to these questions and do the domain questions here. All right, I will supplement with more graphing if I have requests for that, but hopefully you can follow what we did with the exponentials and do it with the log functions as well. Now here are a few follow-up questions that deal with domain. From the start of this lesson, when I had the yellow box, it said that if you have f of x is equal to a log base b of x, that the domain has to be from 0 to positive infinity. In other words, in inequality statements, x has to be greater than 0. Whatever the argument is, it has to be greater than 0. So you can graph this and you can sort of see what the domain is, or you can calculate. You can say x minus 2, the argument, has to be greater than 0. Add 2 to both sides. X has to be greater than 2. They want the answer in interval notation. Greater than 2 is 2 with parentheses toward positive infinity. The next one, I say 1 minus x is greater than 0. Subtract 1 from both sides. You'll have negative x is greater than -1. Divide both sides by -1. When you divide an inequality by a negative, the inequality symbol reverses. So we're getting x is less than negative divided by negative is +1. What is that in interval notation? If it's less than -1, then it is from -infinity to 1. An open interval though, because it does not touch that. That is where the vertical asymptote will be. Now, in these next ones, they ask us to simplify without using a calculator. And what I'm going to do is refer back to what we did in the previous lesson. And remember that if you have log base b of x is equal to y, that you could rewrite that in exponential notation. Base b to the y power is x. The logarithm is equal to the exponent. So here, when it just says log, it is implying base 10. We don't usually write that. Of 1,000 is equal to something, but I don't know what it is. I'm going to rewrite this in exponential notation. 10 to some mystery power is equal to 1,000. What power do you have to raise 10 to get 1,000? The answer is 3. The next one is almost going to seem silly. If you have log, again, it is implied to be base 10. When there is no base, it is base 10. Of 10 to the 12th power is something. Let's put it in an exponential statement. Base 10 to the power, unknown, is equal to 10 to the 12th power. What power do you have to raise 10 to get 10 to the 12th? Well, that seems almost silly. That is 12. The last one of those, we have 10 raised to the log base 10 of 43. This seems very strange. This is, let's write it in log notation. In log notation, it will be log base 10, because this is the base 10, of what is equal to the log base 10 of 43. This log statement is equal to the exponent that you have to raise 10 to get this. The answer is going to be 43. Now, these both seem a little odd, but let me summarize something. If you have log that is a common log of 10 to any power, it is equal to the power. If you have 10 to any log base 10 of an argument, whoops, it will be equal to the argument. These are inverse operations. So if it is common log of 10 to a power, it's going to equal the power. If it is 10 to a common logarithm, the argument of the logarithm will be the value. Let's look at just a couple of application problems. It says the percentage of adult height attained by girls who are X years old can be modeled by. X is the age. X represents the girl's age from 5 to 15. Okay, this is no longer valid outside of that range. Use this function to determine approximately what percent of her adult height girls are at age 15. So what they're doing is saying find f of 15. So I'm going to go to my grapher. I'm going to pull it over here so I can see the function. I'm going to clear this, and I'm going to say 62 plus 35. This is a common log. Instead of x, I'm going to put in 15 minus 4, close. I am evaluating the function, this function right over here. I'm evaluating it when x is 15. So I put my 15 there, enter, and it, let's see, round to 2 decimal places, it will be 98.45. 98.45. What they're saying is when a girl reaches the age of 15, she is reached 98.45% of her height. All right, I believe we have one more question, and it says the loudness level of a sound D in decimals is given by this formula, where I is the intensity of the sound in, here's the units, watts per meter squared. Okay, decibel levels range from 0, which is a barely audible sound, to 160, a sound resulting in a ruptured eardrum. A sound of a certain animal can be heard 500 miles away, reaching an intensity of 8.2 times 10 to the third watts per meter squared. Describe the decibel level of this sound. At close range, can a sound of this animal rupture the eardrum? All right, we're a little unfamiliar, most probably, with this particular formula, but D, oh my goodness, okay, D is equal to 10 times the common log of 10 to the 12th times whatever the intensity is. And I'll just change that into a multiplication symbol there. The intensity of this particular sound is 8.2 times 10 to the third. And that is what I'm going to type into my home screen, and it's going to give me the decibel level. Okay, so off to my calculator. It is 10. Common log, there's log. The parentheses have opened. I put in 10 raised to the 12th power, get out of the exponent, times 8.2 times again 10 to exponent, third power. Get out of there again using the right arrow and close your parentheses. That looks very odd, but it is 10 to the 12th times the intensity. 10 to the 12th times the intensity, which was 8.2 times 10 to the third. Well, I'm glad the calculator has a job of cranking that out. And this is the number of decibels. The instructions tell me to round to the nearest whole number. This will be 159 decibels. At close range, can the sound of this animal rupture the eardrum? The answer would be no, because it must be 160 decibels. So it is almost at the eardrum level, bursting level, but it's not quite there. All right, so those were just a couple of log application problems. You're going to be given the formulas, and it's a matter of being able to type them in on your home screen. All right, if you have difficulty with graphing the logarithms using the tools, you can ask me for more help on that.